Hey, Kristen. Hola. Hey, I heard somebody cough.
Hello.
Hello.
How are you, sir?
I am pretty good. It was a wonderful Easter Sunday.
Well, good. Yeah, we didn't really do anything. I mean, we just were here.
Well, I'm trying to get this whiteboard to come up.
I can see the whiteboard.
Oh, you can see it.
Yes, sir.
Well, I want to see it, doggone.
Oh, well, I don't know how to make you be able to see it. I'm sorry. I can see it, though. It says Monday, April 13th, 2020 Dynamics.
Yeah, good deal. Excellent. Oh, gee. Hey, yeah, that's it. I double clicked and it's all in double clicking, I guess.
Oh, good. I actually had a question.
Sure.
So you have uploaded a folder onto Blackboard now that we're supposed to be submitting our homework to. Is that correct?
Yeah. Now uh, this
Now,
is
so you
this.
want all the homeworks from last week in there?
No, I don't want them.
Okay, you
But
don't want those at all.
no, I'm just trying to get started on that, and somehow you guys are going to send me your homework on Blackboard instead of sending it to me on my email.
Oh, yeah, I understand that. But, oh, I thought you already had, here, I'll make it to where you can see me so you're not just looking at a black thing.
Oh, there you
Um,
are.
Here
Yeah.
I am.
Yeah.
Okay,
Hello.
hello. So I thought you said something about that. I thought I saw an email from you saying that that was already there for us to post to, that it was going to
Uh,
be released at midnight. Did I
yeah.
imagine that?
No, you did not imagine that.
Okay.
And I forget which problem it was, but it's on there. And I want you to do that problem for me.
And then only put that one back on
Yeah.
there?
Yeah. Yeah.
Okay. Okay. So not all
Now,
the other ones.
now, how did this happen? I'm looking at you, Kristen, and I'm up in the corner. I guess I need to click on me again.
Yeah, I mean, you can pin yourself if that's what you want to see.
Yeah, I want to pin myself.
Yeah, I usually
Nothing
I
happened.
pin you too.
Nothing happened.
I don't know. That's very
Oh,
well.
there
I
I
mean,
am.
maybe it's because just me and you are on here. Because like for me,
Yeah.
you're big and I'm small, but
Okay.
I don't need to be big.
Well, I right now I've got my whiteboard
Hmm.
and I'm okay. I wish I had a picture of you on there, but I don't see a picture of you on there.
I don't know. I'm here. I
But
can
you're
see
there.
me.
Well,
Yeah.
let's see. We have 9 minutes before official class time.
Yeah, we have a while. I don't know. Sometimes my computer, it seems like, likes to be difficult and like take forever to load and
Yes,
everything. So I'm just like to go ahead and get in here early and stuff.
right. Hey, I'm going to open these blinds and get a little
Okay.
more light on here. But if there's too much glare, I'll close them.
All right.
We'll see. We'll see how that does. And well, there is some glare. Can you see the glare on that?
Yes, sir, I can. It was actually better before.
Okay, we'll close it. Too much glare. That's too bad. What I need is some curtains that aren't so dang thick. Maybe some white curtains, sort of see-through kind of curtains.
Yeah, there's not a glare now, so it's
Uh,
good now.
we're okay.
Yep.
Well, also, y- these are being recorded. Have you found out that you can look?
Yes, sir. Actually, because my daughter's graduation was last Thursday morning,
Yeah,
and so I wasn't there for strengths for
right.
class. So I've actually already been on the YouTube to watch it.
And you got to see it.
Yes, sir.
That's wonderful.
Yes, sir. I didn't have any problems with it. I went to whatever link
Yeah.
you sent. I don't remember where I got the link from now because I've slept since then. I don't remember if it was on the email or wherever the heck I found the link. But I found the link. I clicked the link and I was able to view the video.
Fantastic. Now, I wish I could see all of the students that are plugged into me, but you're the only one so far. There should be others.
Yeah, I think I'm the only one here because I'm not showing anybody else besides me and you on my screen either. I just think nobody else is logged in yet. I mean,
Well,
it is Monday morning.
yeah,
I mean,
yeah,
people probably don't want to get up and do things yet.
right. Okay, well,
I just have to because I have a really long day today.
now there's a share screen little thing down here. Let me click on that just to see what happens. Share screen.
That's just going to show me what your computer was on your computer screen.
Okay. I don't think that helps me any. And now it does say share down here. I wonder if I click that, what would happen? Uh-oh.
There are other people here. I see
There,
them.
there are other people. Okay.
Yeah, Dalton
Yeah, I
and
just got here.
Daniel.
Oh, yeah, I hear somebody. Well, this says stop share, so I'm going to just stop there. Okay, Dalton, hello.
There we
And
go.
Hello.
And I'm gonna pin you. There
well,
we go.
okay, it's almost time. Let me tell you what we're going to do. I'll tell you what I want to study today. Let's see here. Okay. Yeah, now you had a homework problem. It was 11, I think it was 11:17. Does that sound right? No, 17:11.
Yes, sir. That is the last one I did.
Yeah, and I think we probably should talk about it a minute. Let's do that. While the others are tuning in, we'll talk about 17:11.
Okay. I have to
Now,
get that one back out.
did I put the answer to 17:11 on Blackboard for you guys?
I don't know. I didn't look at that to see if that was there or not.
I don't remember.
I don't remember.
That's
I
okay.
apologize.
No, that's okay. All right, we're going to look at this, and this has got a real long kind of a broomstick affair here, and it's this is 1.2 kilograms, but this one here is 3.6 kilograms, and this distance here is 0.4 meters. And
where did you go?
are you still with me?
I mean, I can hear you, but I don't know what happened to you. Oh, wait. Maybe I clicked something. Sorry. Never mind.
You're
My
okay.
bad. I'm crazy.
Okay. Now this here, this has a middle point. It's it's 0.6 meters here and 0.6 meters here, but they have a 0.0 here at 0.2 meters. And this is 0.4 meters. And this part here is 0.6. This is 0.6 meters here. Now, before we can solve this, we need to find the centroid, center of mass, I guess you could say. Can you guys read all that okay?
Yes, sir.
Okay, we're going to find the center of mass. Let's say that this is the x coordinate, and you could have the y coordinate going up here. That'd be all right. There's x and y. And the centroid would be at 0x times 1.2 kilograms plus 3.6. Wait a minute, 0.6 meters times 3.6 kilograms divided by the total, which is 4.8 kilograms. And so if you solve that, you'll get where the center is, or you'll get where the center of gravity is. And I think it turns out to be 0.45 meters. It's right here, right about here is the center of gravity of that whole thing. Are you comfortable with that center of gravity that I just cooked up?
Yes, sir.
Good, excellent. Well, instead of writing this as 0.6 meters, I'm going to write this as 0.45 meters to here and 0.15 meters to here. I've got this thing broken up into a bunch of distances there. And what we're supposed to find on this problem is the moment of inertia about this fixed pivot. It's called a fixed pivot. Okay. Well, let's do that. You have to take the formula in the back of your book. I wonder what that sound is I'm hearing. It sounds like somebody is sucking on a straw of a strawberry milkshake.
That's very specific. Yeah. Yes.
It might be chocolate or vanilla, but that's what it sounds like. Yeah, somebody just took a nice sip of milkshake. There we go. Who's doing that? But now, see, you have to use the parallel axis theorem on this. And so you go, I'm doing this little guy. And how far is he from O? Well, he's 0.8, I think. He's 0.8 meters. Hey, they quit sucking on their straw. But now, see, you're not through. You got to do the long piece. And so it's 3.6 times, it's 1.2 meters squared. Probably should put brackets right there. But then you have to use the parallel axis theorem. If anyone doesn't, I guess we got two students. We got Dalton and Kristen. If you don't understand any number, just speak up, unmute yourself and speak up. Dalton, are you still there? Earth calling
Yes.
Dalton? Yeah,
Yes, I'm still there.
He's still there. Now we have to use the parallel axis theorem. So we go 3.6 kilograms. But see the distance from this O to the, wait a minute now, we need this, what we need is this 0.2 meters squared. We're doing that broomstick there, and the center of it's here, and we want to find the moment of inertia about O. Now let me look at that and see if I have all that right. I think that's right. I scribbled this down, and I'm going to double check it here. Yeah, that's all correct. And if you do that, you'll get the answer. This is the answer in the back of the book. This is one of those homework problems that you don't have to turn in, because I'm not going to grade it. It's for your learning. All right. Good. Now, I didn't ask you to get the moment of inertia about G. See, this is the center of gravity of the whole thing, but I think we should do that. That term appears in the second law of Newton's second law. Remember, Newton's second law goes like this. We're going to talk about that some more today. And see, that term there appears in Newton's second law. And so I think we should do that too. Okay. So here goes. We're going to do that. Now to do that, these terms here will be the same. So I'll just go ahead and repeat those. You get these from the flap of your book. I don't know if it's the front flap or the back flap. Let me look and see. It's the back flap of your book. About the last piece of information in the whole book. On the back flap. Wait a minute, that's wrong. It goes like this. No, that's right. That's a 1 there. That's right. But what's different is, wait a minute. There's something wrong here. I forgot to put in the, this is wrong, guys. I forgot to put in the 1.2 kilograms here. Just a second. Let me put that in. I think I got that right. Now let me double check. I don't want to lie to you if I can help it. Yeah, that's right. Okay, but now here, what's different here is the distance. See, we're not doing O anymore. We're doing G, and the distance from here to here, it's not 0.8, it's 0.45. So you got to go 0.45 meters squared. Now we're not done yet. We have to add, I just did this little piece. We have to add this big piece. So that's 1/12, 3.6 kilograms. I believe it's 1.2 meters. Yeah, there it is. It's the same numbers we had there. Who else we got out there? We got Kristen and Dalton. Am I just talking to 2 people today? Anybody else out there?
There's quite a few people on here. I can see a bunch of people.
There's
Hello,
13
Professor.
participants.
Oh, I heard somebody. That sounded like Gavin. Was that Gavin?
Yes, Professor.
Well, welcome. Happy Monday, Gavin. And I'm glad there's more people on here. But you all know, or at least some of you know, that you can watch these videos. They're recorded and they're on YouTube. So if you miss one, you can always watch it. Okay, let me finish this up now. Let me see. We're trying right now. I'm trying to find the moment of inertia about the center of gravity for the whole object. And in case you don't know what the heck I'm doing problem. I believe it's 1711. Isn't that the name of it? 1711. That's what we're doing. I asked you to do it. I think I posted the answer even, but I did not ask you for the moment of inertia about the center of gravity. That's what I'm doing right now. Okay, let me finish it. I'm using the parallel axis theorem. And what I need now is the distance from, see, we're doing this long broomstick thing here. I need this 0.15 squared. 0.15 squared. And when you add up all of that, and I got it right, here's what you get. You get 0.772 kilograms per meter squared. That's the moment of inertia about the center of gravity. That's what shows up in this Newton's second law for rotation. Now let me show you one more thing and we'll go on to something else. The parallel axis theorem can also be written like this. Wonder if this is all showing up. I think it's showing up. The parallel axis theorem can be written like this. We'll see. We'll see if it works. Okay. Now we just figured out this, and we figured out this. See, there's I sub O. There it is. There's I sub O. There's I sub G. Da, 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 da. Now the mass of the whole thing is 4.8. Here, let me write this stuff down for you. This will be Ig, which is 0.772. The mass of the whole thing is 4.8 kilograms. Now what this is the distance between O and G. Well, what's that? Well, it looks like 0.35 to me. See, here's O and here's G. Sure looks like 0.35 to me. Now I'm going to put this in my calculator, and if I get I sub O out of it, then we know we did it right. So you can check your work. So here goes. I'm going to plug that in. All right, 0.772, 4.8, 35 squared. Well, boy, Juve, when I plugged that into my calculator, I got 1.36, which is good because that's what I sub O is. Now, one of these days, you're going to have your final exam, and you're going to have to find the moments of inertia about different points. See, this is what they call a physical pivot. See, there's an actual physical pivot right here at O, and this thing swings about that physical pivot. And so you're going to be asked to find the moment of inertia about a physical pivot. But I also might ask you for the moment of inertia about the center of mass of your body. We did both. We found them both, and they are related by the parallel axis theorem. Okay, great. Well, I had fun doing that. And now I'm going to do something else. What we've just done so far, students, those of you that are tuned in, is we have gone over problem 1711. I either have it on Blackboard for you or I will put it on Blackboard for you, but you don't need it anymore because I just did it on my whiteboard. Before we go on, did anyone have a comment or question? I sure wish I could see who was there. I know there's a way. I need one of my daughters, but see, they have to go to work is the thing. One of them's a pharmacist and she goes to work. Hey, there's a thing down here called chat. And a thing here called manage participants. Let me click that and see what that is. Oh, looky here, I got a whole list of wonderful people. Look, I've got Julian and Ross and Allison and Brandon. I'm going to click unmute. There we go. And Cameron, Caitlin, and Dalton, and Eric, Gavin, both Gavins, Christian, and Sam. I guess that's it. It's a pretty good list. Pretty good list of people there. Let me pick on somebody. Let me pick on Caitlin. Let's see, I'm going to click on Caitlin. Nothing happened. Oh, well. I tried to click on you there, Caitlin, but nothing happened. But if anybody has something to say, just unmute yourself and say it, and then we'll move on to the next thing. Oh, wait. This says your speaker is not working. Please check your connection. What do you mean my speaker is not working? Plugged it in. Oh, gee, is my speaker not working? Oh, gee, it says my speaker is not working. The default microphone has changed to microphone blah, blah, blah will now be used.
Yeah, it was popping really bad there for a while.
But
Now
you
it
can hear,
stopped.
you can
I
hear
can
me?
hear you. I can hear you now.
Oh, good. I unplugged it and plugged it back in. This stuff just drives me nuts. I love the academic stuff. It's this computer stuff that I'm nervous about. Can you guys, and you can't relate. No, you guys can't relate. Okay, now next topic, unless you have a comment or question, anyone? Okay, well, we're done with that problem. Let's see what's next here. All right, we're gonna say goodbye to this problem 1711 now. Goodbye, 1711. We had fun with you, but it's over now. Now we had a chapter, I think it was chapter 16, was on rotational kinematics. Chapter 16 was rotational kinematics. But we're in chapter 17 now. And what it is rotational kinetics. Hope you can read my writing. And let me get this off of here, but we have a good crowd here. I just wish I could hear from some of you if you had a question. What happens if I push chat? That might be interesting. But I'm not going to do that now. We're going to move on. What it amounts to, this is kinetics. It's a fancy word for Newton's second law. That's all it is. Fancy word for Newton's second law. And there's three kinds of rotational kinetic problems. Let me list them for you and we'll work on it. Three kinds of N2L rotation problems. Gavin, are you still there? Earth calling Gavin?
Which Gavin?
Either one. I'll take either one. But you're there. Good. Excellent. Okay, there's three kinds of rotational Newton's second law problems. Now, the first kind is where alpha is 0. There is no angular acceleration. We're going to work one of those here in just a minute. Now, the second kind is alpha is not equal 0, but you have a fixed pivot. That's the second kind. It's a little harder. Now, the third kind is alpha is still not equal to 0. You've got an alpha, but there's no fixed pivot. There is
It's like the wheel rolling problems, right?
Yeah, exactly. The third kind is like if you have a wheel that's rolling along. There it goes. Or a bowling ball. You throw the bowling ball. It doesn't have a fixed pivot. However, it can have an ICZV. It turns out that if you're rolling a bowling ball there, the ICZV is that point of contact with the floor. Now, those problems are harder. They get harder as you go down. We're going to do one here, the first kind here in a minute. But while I'm talking about bowling balls, let me show you this. Show you a bowling ball here. So this is where we're headed now. Why did I put 18 there? I don't want 18 there. I want 17. If I goof up, somebody pipe up. Okay. I'm going to draw you instead of a bowling ball, let me just draw you a cylinder, a wheel. It could be like a bicycle wheel, okay? And it's not slipping or sliding. It's rolling about this in, what do they call ICZV? ICZV, that's called the instantaneous center of zero velocity. And there is no velocity for that point because there's no relative motion between the wheel and the surface. However, up here at the top, you have a velocity going, supposed to be flat. It should be flat. There you go. Here at the center, you have a velocity, but it's not as big. It's only half as big because, see, the velocity is equal to, well, the formula is r omega, but the distance from here to here is twice as big as this distance. So the velocity is twice as big. Now here's what's interesting, and the students have a little trouble with. The velocity of a point here is going like that. Because here's your distance r to it. It's not the radius of the circle, but the velocity is always perpendicular to that, and it's there. Now, if you had a point here, I'll show you, the velocity is kind of like, it's perpendicular to that. It's sort of like that. But this should be bigger than this, because every point on here has the same omega. The angular velocity of any point on that bicycle wheel is the same. It's turning so many radians or degrees per second or minute. And over here, here's your radius. Well, we shouldn't call it a radius, but nevertheless, that's how they write that formula. There's your r there, and here's your velocity of a point right there on your bicycle wheel. I hope you understood that. Okay, great. We told you about the 3 types of rotational Newton's second law problems. Now we're going to work one. We're going to work the first type. But I'm going to say goodbye to this. And this is the first kind. This one here happens to be example. It's example 17.5. It's on page 429. So if you have a book, dig out your book and find 429 there. Yeah, there it is. And there's this car there, kind of a sports car affair. And what I want you to do is to draw 2 free body diagrams. So I'm going to do my best to draw 2 free body diagrams. Here we go. There's this one. And then we'll do another one over here. And then I'll try to draw this car here. There it is. Our artist's rendition of that car. Well, I tried. And now we need these distances here. This is, the center of gravity is right here. I wonder why it's kind of back towards the back wheels. But I can't help it. That's what they said it is. This distance from here to here is 1.25. And this distance from here to here is 0.75.
It's one of the cars that has the engine in the back.
Yeah, like a Corvair. Do you guys remember those Corvairs? They had the engine in the back. Don't confuse that with a Corvette. Corvair was nowhere near as nice as a Corvette. Now this distance here, according to this, is 0.3 meters. Now I didn't do this to scale very good. In fact, I did a horrible job. But you guys have rulers and you can draw your diagrams to scale. That needs to be a lot smaller than the 0.75. Okay, great. Now there's 2 diagrams. This is the, it's got a name. Well, it's got the forces. It's going to have the forces on it. And these are going to be kinetic forces. The nose of that thing isn't quite that pointy, is it? Let's try to make that a little nicer. Yeah, there we go. This here is called the kinetic diagram. And it's going to have kinetic forces. This is going to have the forces on it. This is the forces diagram. And I want you to draw two diagrams. The book does. They have them on top of each other here instead of side by side. But the book has two diagrams. See, what this is going to have is forces. Now, I like my forces in red, and my wife found a red pencil. I don't know how good it is, but we'll try it. This is going to have a weight. Oh, gee, that's not very dark. Well, we tried. Forget it. It's red, but you can't even see it. Let's just put it in black, I guess. Now that weight's going to be, what's the mass? 2 megagrams, so that's 2,000 kilograms, right? Yeah. What's 2,000 times 9.81? Okay, guys, the weight of this thing is 19,620. It's 19,620 newtons. Now it has a force here going up and a force here going up. We'll call this force A and B. There's A, there's B. Getting kind of messy here. This is supposed to be 1.25 meters. And that's supposed to be 0.75 meters. Okay. Now there's going to be another force because it's a rear wheel drive. Read it. It's a rear driving wheels. Yeah, rear wheel drive. And so there's going to be a force here. It's a frictional force. We'll call this B. And this is a frictional force. Now, here's my question to you guys. Does that frictional force push the car to the left, or does that frictional force push the car to the right? Now, here, let me call on somebody. Here we go. We'll call on my friend. Hey, Brandon, are you there? Unmute. Brandon, are you there? Earth calling Brandon.
Yes, sir.
Yeah, Brandon, I want your opinion now. There's a frictional force on this rear tire. It's rear wheel drive. Is that force going to go to the left, or is it going to go to the right, Brandon?
The force of the friction is going to go opposite the direction of the car. So if the car is going left, the force should go right.
Okay, now Brandon says the force is going to the right. Now the thing is, Brandon, there is a force going to the right, but it's on the road. The force of friction on the road is going to the right. I want to know the force on the car. It's going to the left. So I hope the rest of the students understand that this frictional force is going to make the car go to the left. But thank you, Brandon. It's okay. But he's right about that opposite business. How does that go? The opposite, the force of friction is, I forget. But I do know that force makes the car, see, the car's going this way. In fact, here's the acceleration of the car. Here's your MA. Now that's called a kinetic force. See, these are forces. A is a force, B is a force, the weight of 19,620 newtons is a force, and the friction is a force. Those are forces. This MA, if you can read my writing, is called a kinetic force. This is the kinetic diagram. Now, in these kind of problems here, I alpha is 0. Remember, there's 3 kinds of kinetic problems that we are going to study. The first and easiest is the kind when alpha is 0. Alpha is 0, so I alpha is 0. Because I times a 0 gives you a 0. And what we're going to use is this equation here. Well, we're going to use Newton's second law. There's one that goes like this. And then there's one that goes like this. But the beauty of this one is it's 0 because there is no alpha. We do not want this car spinning this way, kind of like at the Indianapolis 500 when the cars go wild and they just start cartwheeling up into the crowd and head over heels. The car is going head over heels, and by the time it stops, there's not much left of the car except the cage that the driver's in, and sometimes they get up and walk out. So these are the 2 equations. We're going to write them now, and we're going to get our answers, and we'll see if we can get the answer they got. Okay, well, let's first of all do the sum of the forces in the x direction. Here we'll put G, yeah, we'll do the forces in the x direction. Here we go. Well, there's only one, and guys, I'm going to make this my x direction. Car's going that way. And we have F equals MA. I think it's 2,000 kilograms. Isn't that what this thing is? 2,000 kilos? Yeah. Times A. Well, I don't know F and I don't know A. However, they did tell us that the mu sub K is 0.25. So we could write this F as 0.25 times B, where that's the normal force on the rear tires. So we have a lovely equation here. And I think this is what they want. They want the acceleration of the car. Isn't that it? Let me read it. Let's see. Yeah, that's what we're after. Okay, now we're going to write this equation here. Well, the moment's about G. Well, here's G. G is the center of gravity. And we have a minus A times 1.25 meters plus B times 0.75 meters minus F, which is 0.25B, times 0.3 meters equals 0. Okay. Now, I'm going to ask one of my students, how come this moment is negative? Let me pick on Cameron. Earth calling Cameron.
Yes.
Cameron, let me, yeah. Cameron, how come that moment of A times 0.125 meters, how come it's negative, Cameron?
Honestly, I'm not 100% sure.
That's fine. That's what you're here for. That's why you're here. Moments are negative, Cameron, if they're, it's either clockwise or counterclockwise. Which is it?
It's clockwise, right?
Yeah, there you go.
Okay.
can you see that this A here, pushing up here, gives you a clockwise moment about your G?
Yes.
Yay, good going. Well, let me pick on Cameron some more here. He's doing a fine job. Cameron, how come this moment here of B acting at 0.75 meters is plus? How come it's plus, Cameron?
It's plus because it's going counterclockwise.
He's got it. Now, do you see this 0.25 B here? What that is the friction. And
Okay.
it's acting at 0.3 meters, and it's a negative. Cameron, how come that's a negative moment?
Because it's going clockwise.
Yeah, good going.
Okay.
Good going. Okay. Well, we're almost done here, guys. And what we're going to do now is we're going to write the Newton's second law in the y direction. Well, in the y direction, we have A plus B going up, and we have the minus 19,620 going down, and it's equal to 0 because this car does not go up or down. It just stays going level. Now I'm going to circle these two equations. Well, it's not exactly a circle, but I'm going to put those in a box there. And y'all, little Southern talk, y'all can see that we have two equations and two unknowns. Because look, A is an unknown, B is an unknown. There's B again. There's A, there's B. There's only two unknowns and there's two equations. You can solve that. And instead of me doing a bunch of algebra and boring you even more than I am, I'm just going to give you the answers. Here we go. I'm going to give you the answers. It turns out that A is 68, 80 newtons. B is 12,740 newtons. Those are the answers when you solve those equations. And I know you took algebra and you don't need me to show you how to do algebra. All right, now once you get that B, look here. You can plug that in here now and solve for the acceleration. Here goes, I'm going to do that now. And I got an acceleration of 1.5925. And if you don't believe me, then you should you get your calculators out and do that yourself. Okay, now let's see what the answers are. They have the answers because this is an example. And they said the acceleration is, the book says acceleration is 1.59 meters a second squared. Well, that's what we got. It's just that they rounded off to 3 digits, which is fine. Okay, well, there's that one then. We've done one of those. And I just want to see something. I want to go and see if this is on Blackboard. I wonder if this says share screen. I don't know what I'm doing, guys. That's the problem. Share. Let's push share here and see what. No,
Yeah, that works.
new,
It's sharing your screen now.
yeah. I don't know what I'm doing. Let me get out of here. I don't know what I'm doing. I wanted to show you. if I had this on Blackboard. Uh-oh, I'm back to Google now. I don't want Google. Oh, gee, total disaster here. Do I want to get out of Google? Oh, man. Ah, gee. I'm gonna have to start all over again. Just a minute, guys.
Perhaps you want to stop screen sharing until you have it ready.
Oh, maybe that's it. Yeah, stop screen share. Okay, hey, I'm back with you. I need to get one of my daughters to help me with that, Jazz. It's out of my league. Okay, now the next topic is the PixPivot. Not PixPivot, fixed pivot type of problem. Remember, there's three kinds of problems that I told you guys about? Well, we're going to do a fixed pivot problem now. And let me see where it is here that I want to do. Okay, yeah, I found it. All right. Well, I'm gonna erase all this, Jazz, unless somebody desperately needs to ask a question. Okay, well, I'm gonna erase all this. Now remember, there's three kinds of rotational what's the word? Kinetic. Three types of rotational Newton's second law problems. The first kind is when alpha is 0, and we just did that. The second kind is alpha is not 0, but you have a fixed pivot. And then the third kind, some books call it general motion. It's a little more complicated, but it's not going to scare us. Okay, so I picked out a problem here, and this is problem 1758. So we're going to try to do 1758, and it's one of these babies. Alpha is not 0. You got an alpha. This thing is going to rotate. It's going to have an angular acceleration, but it's got a fixed pivot. So let me draw it for you. That was a review. I already told you that once, but maybe it doesn't hurt to tell you stuff over and over. Okay, now, how many diagrams are you guys going to draw on this stuff? We're going to draw 2, Mr. Griffin. You're going to draw 2 diagrams. That's what you're going to do. One of them is for something, and the other one is for something else. Do you remember why are we doing 2 diagrams?
Oh, one's for the forces, and then the other one is for the kinetics.
You got it. One is for the actual forces, and the other one is for the kinetic forces. And one is the one on the left would be for actual moments, and the one on the right would be for kinetic moments. There's 2 kinds of kinetic moments. Let me write them for you. See, this one here is for forces and moments. And you know what forces are, and you know what moments are. But this one is for kinetic forces. And those are MAs. Maybe nobody ever told you that an MA was a kinetic force, but that's what it is. And maybe nobody ever told you that I alpha is a kinetic moment, but there's two kinds of kinetic moments. There's that kind, and there's that kind. See, this is an actual moment. You have to specify about what. Now, the center of gravity here would be right there. There's your center of gravity, and it's right there. And you have to say the moment of inertia about a point, and the acceleration at that point. You have to specify that. You have to put your little subscripts in there. Okay, now let's see what it says here about this problem. They said this is 0.5 meters, 0.5 meters, 0.5 meters, 0.5 meters, same thing. 24 kilogram plate. Let me write that down someplace. 24 kilogram. So we could multiply by 9.81. Let me do that. 24 times 9.81 is, I sure wish that red color would work, but dang it, maybe if I shake it like a thermometer, huh? We'll see. No, it's worthless. No good. But I can tell you what this force is. It's 235.44. 235.44 newtons. Now there's going to be some forces acting on this fixed pivot. See, that's a fixed pivot. That's a fixed pivot. And there's going to be some forces. I think there's going to be a force going up on that fixed pivot. But I also think there's going to be a force going to the left on that fixed pivot. We could give it names. How about we could call this AX maybe, and AY. Those are nice names. We could have our x-axis going this way. We can make it any way we want. Now here's why I had that going to the left. See, what this thing's going to do is it's going to try to spin, and it's going to start off spinning that way because it has to. It rotates about that fixed pivot. And we know that the sum of the forces on a body is equal to the mass times acceleration. Can you see that this AY is going to have to be smaller than the 235 to give you a net force going down? This has a component going down. Can you see that force, if it goes to the left, this has a component going to the left? See, if you write this in the x direction, that's a vector equation, but in the scalar equation, see, the sum of the forces in the x direction is going to the left, and the sum of the MA, the kinetic forces, has to go to the left too, because see, that's an equal sign. Equal sign means if you got stuff going to the left on one side of the equation, then it's got to go to the left on the other side. I'm drying up, just a minute. Yeah,
Hey, Professor.
yeah, I'm listening.
Couldn't you find the components by just making that a 45-degree right triangle and getting the x component of the g?
I like that very much. I like that very much. There's a 45-degree angle right in here. You can see it. There's a 45-degree angle. So when we go to write this equation, here's what we're going to have. We're going to have AX going to the left equals, forget what it is. Is it 24? It's 24 kilograms times. Now what this is an MA. And it's going to be MA. Well, we already know M. It's, oh, we already wrote that. It's 24 kilograms. But see, it's going to be A cosine of 45. It's a component. See, here's your A. Okay, well, there's a nice equation. Trouble is, we don't know what AX is, and we don't know what A is. However, we do know A is equal to R alpha. It's one of our equations that we know and love. But see, the R here, I got to figure what that R is. And let me think and think and think. Now, let's see. This is 0.5. That R is equal to, let me write it over here. It's I think it's 0.25 times the square root of 2. I think that's what I think it is. Let's see. 0.25 times the square root of 2. This distance here is 0.35355. So the acceleration is equal to 0.35355, those are meters, times alpha. We don't know what alpha is. But we're not done yet. All we've done so far is just write the x component of Newton's second law, F equals ma. Why don't we do the y component? Here we go. What I'm going to do now is the sum of the forces in the y direction equals ma y. All right. Well, what do we got in the y direction? A little more stuff going on. We got, tell you what, I think I'm going to have y going down. This is my problem. I can have y any way I want. I'm going to say y is going down. So if y is going down, what we have is 235.44 going down minus ay is equal to the mass times a sine of 45. See, what we're looking at now is the going down component. It's ma sine 45. Well, we got another nice equation there. But we don't know what a is, and we don't know what ay is. We're just kind of in trouble. But we're not done yet. We have another equation that goes like this. The sum of the moments about g is equal to ig of times alpha. I think we can get this ig from the back of the book. And I think we can maybe get that. It's going to be a little bit ugly. But we could get it. Here, let me write it for you. The moments about g are 0.25 AX, it's a positive, minus 0.25, those are meters, times AY. I think we're done. I think that's all the moments about G. You see that 235 newtons? That doesn't give you a moment about G. Let me ask somebody that. That'd be fun to ask. That's a good question to ask. Daniel, unmute. Daniel, are you there? Earth calling Daniel. I wish I could click on him and see his picture. He's not going to answer me. Well, that's okay. Let's pick on Kristen. I bet she'll answer me. Hey, Kristen. Come in, Kristen.
Yes, sir.
Oh, she's there. Yeah. I was going to ask Kristen a question, but I forgot what the question was. Does anybody remember what I was going to ask you, Kristen?
No, sir. I don't know what you were going to ask me.
Oh, that's okay.
That's okay. I probably wouldn't have known the answer anyway.
I bet you know this. Kristen, you see this positive, this is a positive 0.25 AX. It's a moment. Now the 0.25, that's this distance from here to here. It's 0.25 meters. Because see, it's a half a meter square. It's a half a meter square, and you got half of that, so it's 0.25. Hope you can read my writing. How come that moment's positive, Kristen? Oh, wait a minute. Yeah, it is positive. How come it's positive?
Because it would rotate counterclockwise, and anytime it rotates counterclockwise, it's positive.
Good going. Excellent. Excellent. And Kristen, how come this is minus 0.25 AY?
Because it would rotate clockwise.
She's got it. Now, here's what I was going to ask Kristen. There's another force here. It's 235 something newtons. It goes through G, but it doesn't give you a moment about G. Notice, that's it. Here's
Right.
the equal sign. How come I don't have a moment for that, Kristen?
Because it intersects the line of action. With the line of action, so you wouldn't create a moment.
That's a good enough answer for me. She understands. She understands. That force goes through G, so it doesn't give you a moment about G. But now those two forces, they don't go through G, and they give you moments, and here they are. And we're going to write up these equations now. Now here's this equation here. Let me box these up. You're going to get confused. There's that equation. And then there's this one here. And then there's this one here. Now I can get this I thing. I'm going to circle that. I can get that. And oh, hey, there's another equation here. Now I have four equations, and there's four unknowns. The unknowns are A and alpha, AX and AY. AY, AX. There are four equations and four unknowns. We could solve that, and we could get AX and AY and A and alpha, couldn't we, students? Yes, we could, Mr. Griffin. But we don't want to because it's too hard. There's an easier way. Let me show you the easier way. But before I do, let's get this I. I put a circle around it telling you that I think we can get that. But you got to go to the flap of your book and get it. Now I'm going to erase all this stuff, but you could do the problem that way. Couldn't you? It's just a chore. I'm going to show you an easier way, but let me erase this stuff. We're going to find that I. For those of you that just tuned in, you wonder what the heck is he doing now? We are doing problem 1758. It is on page 449. And I just showed you how to do the problem, but we need this I. Now, if you go to the back of your book, back flap of your book, it says 1/12 m a squared plus b squared. Go to the back flap of your book, see if you can find that equation. Boy, Jove, I just found it. It's back there. Well, let's do it. 1/12, 24 kilograms, 0.5 squared plus 0.5 squared. Okay, we're going to get I now. So that would be 2 times 0.5 square plus 0.5 square. Holy cow, I get 1. I'm going to wait till,
That's what I got.
yay, that's what I got. I got a 1. That's easy. Now with that, I just showed you 4 equations with 4 unknowns. And you plug in that 1 there for I, and you can solve it and get your answers. But there's an easier way. And let me talk about that now. Help me remember that that came out to be a 1. Now it's got units. It's kilogram meter squared. What's going to happen to you on your final exam if you don't put down units? Something bad happens.
We're gonna get
Get
points
your
taken
points
off.
docked.
Yeah, I'll dock you a point. Okay, now let me give you the 3 Newton's equations for the sum of the moments. This is the one that I've given you, I think, today before, but there's 2 more. There's one that goes like this. And then there's one that goes like this. These are in your book, believe it or not. Now these P's are points other than the center of gravity. They can be anywhere, any place you want. I hope you can read my writing. Now, I would like for us to be able to use all 3 of these. What these are is Newton's second law for rotation. They're Newton's second law for rotation, and I want us to zero in on this 3rd one. This 3rd one has an acceleration of the point P, which can be any point you want, and I'm going to pick this point A here. And see, the acceleration of that fixed pivot is 0. So this term goes bye-bye, because that's a 0. That's a mass times 0. So this term is 0. And you come up with this lovely equation here. And you'll find that that equation is a lot easier to work with than that 4 equations and 4 unknowns that we had a little minute ago. How are we doing on time here? Holy cow. Time goes by fast when you're having fun, you know it?
Yes, Professor.
And here's the thing. We're going to meet every Wednesday and at 9:30 every Monday, every Wednesday, 2 times a week, we're going to meet this class for 3 weeks. And then I think the semesters, that's it. Then we'll have your final exam. So I'll be seeing you again this coming Wednesday. Now I put some homework on the blackboard there for credit. We're actually going to grade this one. Read the blackboard. It's under content. And you can send that homework into me in Blackboard if you're techie. I'm not really exactly sure how you're going to do it, but my daughter's informed me, oh, your students can do that. So it's new to me, but we're gonna start grading homework again. But I just don't want 100 emails a day coming in on my email. We're going to do it through Blackboard. Okay, now we're going to use this equation here now, and let me erase this so I can have some room to work, and we're going to use it. Here goes.
So why was acceleration at P0?
If you pick P to be your fixed pivot, put that pin right there. It's a little steel pin. Put a little oil on it so that the body can rotate nicely. And I want you to tell me what that pin is doing. It's not going anywhere.
Yeah, it's not moving.
It's not moving. It's certainly not accelerating, is it?
Okay, that makes sense.
Thank you for asking. That's a good question. Okay, now here's our equation now, and you'll see this equation in the book. I could find it, I suppose, if I dug around. But we need the moment of inertia about, we don't want P, that's just a dummy variable. We want it about point A. Okay. Well, I'll tell you what it is. We're going to get that. The moment of inertia about A is going to be well, you have to get the moment of inertia about the whole dang thing. Moment of inertia, no. The moment of inertia about G plus the mass times the distance squared between A and G. They have a name for this equation. It's called the parallel axis theorem. Now, we've already done that, and I think I scribbled it down someplace. Let's see. Did I? Or did I not? Gee, I don't remember.
It was 1.
Oh, yeah, that's what it was. Good going. Good going. Proud of you. It's 1 kilogram meter squared. We did that. And I think this is 24 kilograms. But now see this distance between A and G, I did that too. I think that was the point 35355, wasn't it? Anybody, do I need to go back? Yeah, there it is, 0.35355. Do I need to go back over how come that distance is point? I'll be glad to. Does somebody speak up?
Yes, please.
Go back over it. Okay. There's a little triangle here. Thank you for asking. That little triangle has 0.2 meter to 0.25 meters, 0.25 meters. And
So it's a
Pythagoras,
special triangle. Okay.
yeah, you don't need me anymore?
No, that makes sense.
See, they don't need me anymore. They can get that. They don't need me to do Pythagoras.
I looked away and I looked up and there's a square root of 2 and I was like, where did that come from?
Well, you do that and make sure that I did that right. I'll stop. I'm going to do it too to make sure it's right. 0.25 squared plus 0.25 squared square root. Boy, Jove, it's 0.35355. Okay, we're doing great, I hope. All right. Well, let's get this then. I'm trying to get this. And here we go. It's going to be 1 plus all of that. So I'm going to do that now. Hey, I got 4. Anybody else out there get 4?
That's what I got.
Yay. Okay. Now let's write this equation. Only we're doing them about A here. P is just sort of a dummy variable. And we're taking our moments about A. Well, these two forces here go through A, so they don't give you a moment. But I tell you what you'll get. I'm just going to write these as clockwise. They're both clockwise. Technically, that's a minus moment, but there's just one, so they're both clockwise. And so what you get is 235, 44 newtons times 0.25 meters clockwise equals 4 times alpha. Do you remember a while ago we had 4 equations and 4 unknowns? Look at here. We have 1 equation with 1 unknown. Isn't that a lot nicer? It's a lot nicer. Now we're going to get.
Yes, sir.
Oh yeah,
I agree, Professor.
I agree. It's nicer. Here we go. We're going to get alpha now. 235.44 times 0.25 divided by 4. Ta-da! We have now figured out alpha. Alpha is 14.715 radians per second squared. And now we can get a little a. See, the acceleration here is equal to r alpha. It's equal to 0.35355 alpha. And we can get it. Now here goes. I'm going to do it now. Times 0.35355. I'm getting 5.20 something or other meters per second squared. Hope you can read my writing. But we have the acceleration now of the center of gravity. We have alpha, the angular acceleration. And we can get AX and AY. I think that's what they wanted. They wanted AX and AY. I think. Let me read it. Determine the initial angular acceleration. Yeah. There it is. There it is. There's part of the answer. Now let's go to the back and see if we got that alpha correct. I'm going to go to the back. We're going to see if we got that correct. What was this? 1758. 1758. 1758. They said alpha is 14.7. The book says alpha is 14.7. And of course, it's clockwise. You can see it's going to rotate clockwise. Hey, we did good. They just rounded off, and we did great. Now, they also wanted these forces here. I had the equations, but remember, there was 4 equations and 4 unknowns, and I erased them to give me some room. But if you'll take that alpha and plug it back into those equations, you can get AX and AY. And I think you're all set. Now, we've been together till it's 10 till 11. Theoretically, our class is coming to an end now. And I gave you some homework. What was the homework I gave you? Let me think about this a minute. Gee, I hope I didn't just do the homework and spoil your fun. No, I didn't spoil your fun. I don't think I spoiled your fun. Yeah. Now you can look this up on Blackboard, but I'll just tell you what it is. Your homework is, I need a little room here. I'll say goodbye to this. We had fun with that. Your homework is R17-3. It's on page 470. You'll find it on Blackboard. I'm going to grade it for points. You're going to submit it on Blackboard. That is, if you can figure out how to do it and I can figure out how to get it. So we're starting something new now. I know I'm slow at this and I know we're kind of behind, but I'm doing the best I can, all right? And I want you to do this homework and try to submit it on Blackboard. And read the instructions there. It should be under content. It might be under assessment and click on assignment. I'm not sure.
It's at the very bottom of content.
It's at the very bottom of content. Thank you. Well, I've had a lot of fun here. And what are we going to do Wednesday? Wednesday, let me see what we're going to do.
Professor,
Yes.
are you wanting us to submit through just sending you an email through Blackboard, or are you wanting us to submit, like, where are we supposed to submit this?
Oh, I wish I could answer that.
He said there's a folder there
Yeah.
that you can submit into on Blackboard.
Where is that?
Okay,
On-
so go.
Go to
Yeah.
content on Blackboard and you scroll down all the way to the bottom. It says homework and and then underneath it says R17-3.
Yeah.
If you
Page
click on
470, submitted through Blackboard, but where on Blackboard?
Yeah, so if
Click-
you click the homework thing itself, you can it'll actually bring you to a new page because it's underlined and stuff. And then
Okay.
when you go in there, you can attach a homework file into the submission.
Yeah.
Okay.
Somehow you're going to need to make a homework file, I guess.
Well, you just have to do the homework and make a image file or a
Yes.
document
Yes.
file.
Well, bless you guys for being able to figure that out. And what are we going to do? Well, next time you might want to read about, remember I told you there are 3 kind of problems? This is the 3rd time I think I mentioned that. The first kind is when alpha is 0. The second kind is a fixed pivot. And we just did one of those, fixed pivot. And then the third kind is general motion. And if you'll read about that, it starts on page 456. You could read about it. It wouldn't hurt you any. Page 456. I bet that's what we'll be doing on Wednesday at 9:30. Okay, guys, that was fun.
Bye.
Bye-bye.
See you at 1.
I'll see. Yeah, I'll see you at 1. Exactly. If I can figure out how to get out of here, which I'm not sure I will. All right. Okay. Yeah. Yeah, I remember now. Okay. End meeting. There you go. And